The zero law of thermodynamics. Temperature. Mechanics deals with the mechanical energy of system and is governed by Newton's laws. Thermodynamics deals with an internal energy of the system, thermal energy, and is governed by a new set of laws. The central concept of the thermodynamics is temperature. Temperature is one of the 7 international system-based quantities. Physicists measure temperature on the Kelvin scale, which is marked in units called kelvins. Although the temperature of a body, a period has no upper limit, it does have a lower limit. This limiting low temperature is taken as the zero of the Kelvin temperature scale. Room temperature is 290 Kelvin. This is the Kelvin. When the universe began around 137 billion years ago, its temperature was about 10 to the 39 Kelvin. As the universe expanded, it cooled, and it has now reached an average temperature of about 3K. We on Earth are a little warmer than that because we had lived near a star. Without our sun, we too would be 3K, or rather, we would not exist. The lowest temperature reached in lab up to now is T equal to 0.38 times 10 to the minus 12 K at University of Bremen, Germany, which is published on the 30th August 2021, Physics Review Letters. Temperature is one of the 7 international system-based quantities. Physicists measure temperature on the Kelvin scale, which is marked in units called kelvins. Although the temperature of a body, a period has no upper limit, it does have a lower limit. This limiting low temperature is taken as the zero of the Kelvin temperature scale. Room temperature is 290 Kelvin. The zero law of the thermodynamics. The property of many bodies changes as we alter their temperature. In thermal equilibrium, all physical properties of matter, of system, are stable. That means they does not change with time. The zeroth law of thermodynamics. If bodies A and B are each in thermal equilibrium with the third body T, then they are in thermal equilibrium with each other. Now, body A is in equilibrium with thermal T. Body B is in equilibrium, thermal equilibrium with system T. Then, if we touch A and B, nothing will change. They are in thermal equilibrium. In less formal language, the message of the zeroth law is everybody has a property called temperature. When two bodies are in thermal equilibrium, their temperatures are equal, and vice versa. The zeroth law, which has been called a logical afterthought, came to light only in the 1930s, long after the first and the second law of thermodynamics has been discovered and numbered. Because the concept of temperature is fundamental to those two laws. The law that established temperature as a valid concept should have the lowest number. Here, the zero. Measuring temperature. The triple point of water. To set up a temperature scale, we pick some reproducible thermal phenomena and quite arbitrarily assign a certain Kelvin temperature to its thermal environment. That is, we select a standard fixed point and give it a standard fixed point temperature. liquid water, solid ice, and water vapor, gaseous water, can coexist in thermal equilibrium at only one set of values of pressure and temperature. The temperature is 233.16 Kelvin. The pressure is 0.61 kilopascal. This is the bulbs. This is the ice, water vapor. Figure shows a triple point cell in which the so-called triple point of water can be achieved in the laboratory. By international agreement, the triple point of water has been assigned a value of 273.16 Kelvin as the standard fixed point temperature for the calibration of thermometers. The pressure is 0.61 kilopascal. That is, T3 equals 273.16 Kelvin, called a triple point temperature, in which the subscript 3 reminds us of the triple point. This agreement also set the size of Kelvin as 1/273.16 of the difference between the absolute zero and the triple point temperature of water. The degree of Kelvin is equal to the degree of Celsius. Note that we do not use a degree mark in reporting Kelvin temperature. This one, okay. It is 300 Kelvin, not 300 degrees of Kelvin, and it is 300 Kelvin, not 300 degree Kelvin. The constant value gas thermometer is chosen as a standard thermometer to calibrate other thermoscopes. This is a constant value gas, this is a constant value. The gas inside, okay? This is label 0, so the gas is always this constant. The constant value gas thermometer is chosen as standard thermometer to calibrate other thermoscope. Okay, we look at this. This is constant value. This is the temperature you want to measure. Okay, this is called a mercury reservoir. It can move up and down, up and down. Okay, this is a gas-fed bulb. This is the one. Okay, made of glass, quartz, or platinum. Depends on the temperature range over which the thermometer is to be used. Okay, yeah. Now connect to a tube to a mercury manometer. Okay, by raising and lowering reservoir R, the mercury level on the left can always be brought to the zero of the manometer scale. So in this case, the volume is constant. Ensure the volume of the confined gas remains constant. We see this is the volume is constant, okay? And on the constant volume, the temperature is proportional to the pressure, okay? This is measured in Kelvin. This is constant. Okay. If we measure the triple point of water, okay? This is the P, the pressure of the gas, constant volume gas. The P plus rho GH equal to this one. This is the P0. P0 is atmosphere, okay? Then when do the triple point of water temperature, P3 equal to C, I can get the P3. This constant is equal to this constant. So we put this one inside, we get T equal to Cp. This is C equal to T3 over P3P. And T3, we know that one is 2 point, that a triple point of water, this is 273.16 Kelvin. So this is a P over P3. Now, when we do the measurement, we find if we use different mass, the gas are a little bit different. Okay, if we use a different kind of gases, the measurement are different. So we have a little bit of trouble. And then we find out if we take the mass of gas is as less as possible. That means this is under condition limited m approaches zero. Whatever gas we use, we get the same answer. So this should be the gas is as less as possible. Okay? If temperature is to be a truly fundamental physics quantity, it is absolutely necessary that its definition be independent of the properties of the specific material. Okay? We choose the gas thermometer as our standard instrument precisely because no such specific properties of materials are involved in this operation, as we mentioned before. Use any gas, you will always get the same result. The condition is the mass is approached to zero. Okay? And we found when you measure the boiling water with the nitrogen, helium, hydrogen, they get the same answer, as long as the mass is approached to zero.
The electrical resistance of most materials increases when they are heated. Here is a device known as a thermistor that shows the opposite effect. At room temperature, the thermistor has a resistance of about 12,000 ohms, as shown on this ohm meter. When the thermistor is heated by squeezing it between two fingers, its resistance decreases dramatically. Dipping the thermistor in ice water to cool it increases its resistance.
This is some corresponding temperature. Boiling point of water, 100 degrees Celsius. This is 212 degrees of Fahrenheit. Okay, the freezing point of water is 0. Okay, and is a 32 degrees of Fahrenheit, and so on.